Hello everyone, welcome back to the Simple Spark YouTube channel. In our last few videos, we covered the basics of light, reflection and refraction and also about the lens. Now we are diving into some of the most important tools for solving lens problems, sign conventions. Think of sign conventions as the rules of the road for physics problems. They help us keep track of whatever value is positive or negative, which is crucial for getting the right answer. We will be using the new Cartesian sign convention. The most important rule to remember is that we always place the object on the left side of the lens. This means light travels from left to right. Let's break down the rules. First, every measurement you take, whether it is for the object, the image, or the focal length, must start at the optic center of the lens. Second, any distance we measure to the right of the optical center is positive since that's the direction of the light is traveling. Distances measured to the left are negative. Finally, for heights, anything above the main horizontal line, the principal axis is positive and anything below it is negative. With our sign conventions in place, we can now introduce one of the most powerful equation in optics, the lens formula. This formula connects the object's position, the image position, and the focal length of the lens. It is written as 1 over V minus 1 over U equals 1 over F. Remember, U is the distance of the object from the lens and V is the distance of the image. The F is the focal length. You can use this formula to find any of these values as long as you know the other two. Just be careful to the use of the correct signs. Magnification represented by the letter M tells us how much larger or smaller an image is compared to the object. It also tells us if the image is inverted or upright. We can calculate it in two ways, either by dividing the image height by the object height or by dividing the image distance by the object distance. If M is positive, the image is upright and virtual. If M is negative, the image is inverted and real. Now, let's talk about the power of a lens. The power of a lens is measured of its ability to converge or diverge light. The shorter the focal length, the more the lens bends light and the greater its power. We calculate power using the simple formula P equals to 1 over F. It is super important here to remember that the focal length must be in meters. The unit for power is diopter, abbreviated as capital letter D. For a convex lens, power is positive and for a concave lens, power is negative. The sign of the power of a lens tells us what type of lens it is. When the power is positive, it means the lens is convex. Convex lens converge light rays to a focal point. This positive power corresponds to a positive focal length, meaning the lens bend light rays inward. On the other hand, when the power is negative, the lens is concave. Concave lenses diverge light rays. A negative power means the focal length is negative, indicating the lens spreads the light rays outward. For example, a lens with power of plus 2 diopter has a focal length of plus 0.5 meters. This means it is a convex lens that focuses light at half a meter. Conversely, a lens with power of minus 2.5 diopter has a focal length of minus 0.4 meters. This is a concave lens that causes light to diverge as if some coming from a point 0.4 meters in front of the lens. Understanding the sign and value of the lens power help us identify how lenses will affect light and images in optical devices. When multiple lenses are placed in contact with each other, their combined effect can be described by the total power of the combination. The total power represented by the letter P is simply the algebraic sum of the powers of each individual lens. If we have lenses with powers P1, P2, P3 and so on, then the total power P is calculated as P is equal to P1 plus P2 plus P3 so on. This means we add the powers of each lens together, taking into account their signs, positive for convex lenses and negative for concave lenses. The resulting total power determines the overall focusing ability of the lens combination. Now let's some of the problems. In the first problem, a concave lens has focal length of 15 cm. At what distance should the object from the lens be placed so that it forms an image at 10 cm from the lens? Also find the magnification produced by the lens. First of all, see what is given. The image distance V is negative 10 cm. The focal length F is negative 15 cm and we need to find the object distance U. Using the formula 1 by V minus 1 by U is equal to 1 by F, 1 by V is equal to 1 by V minus 1 by F. Substitute the given values. So 1 by U is equal to 1 by minus 10 minus 1 by minus 15. Simplify. 1 by U is equal to minus 1 by 10 minus into minus plus 1 by 50. Finding a common denominator we get, or finding the LCM we get 30. So 1 by U is equal to minus 3 plus 2 divided by 30. The answer will be minus 1 by 30. 1 by U is equal to minus 1 by 30. Therefore U is equal to minus 30 centimeter. Next, magnification. M is calculated as the ratio of image distance to object distance. So M is equal to V by U is equal to minus 30 by minus 30. Minus 10 by minus 30, 1 by 3, which is approximately 0.33. The positive sign of magnification indicates the image is erect and virtual. Also, the image is 1/3 the size of the object. Next problem. A 2 cm tall object is placed perpendicular to the principal axis of a convex lens of focal length 10 cm. The distance of the object from the lens is 15 cm. Find the nature, position and size of the image. Also find its magnification. First let us see what are given terms. The object height h is 2 cm. The focal length f is plus 10 cm and object distance u is minus 15 cm. We need to find the image distance v and image height h dash. Using the lens formula 1 by v minus 1 by u is equal to 1 by f. Rearrange 1 by v is equal to 1 by f plus 1 by u. Substitute 1 by v is equal to 1 by 10 plus 1 by minus 15. So we will get the LCM as 30 and therefore 1 by v is equal to 1 by 30. Therefore the image distance v is equal to 30 cm. V is equal to 30 cm. Calculate the m. M is equal to h dash by h is equal to v by u. So rearrange h dash is equal to v by u into h. Substitute the values of v, u and h. 30 by minus 15 into 2. So we will get minus 4 cm. The magnification is m is equal to h dash by h is equal to minus 4 by 2, that is minus 2. The negative sign indicates that the image is real and inverted. Also, the magnitude of magnification shows the image is 2 times larger than the object. Consider the next problem. An object 5 cm in length is held 25 cm away from a converging lens of focal length 10 cm. Draw the ray diagram and find the position, size and the nature of the image formed. Given the object height h is 5 cm, object distance u 25 cm, that is minus 25 cm, and focal length f is 10 cm. We need to find the image distance v and the image height h dash. Here u is negative because object is to the left side of the lens and f is positive because focal length is on the other side of the lens. Formula 1 by f is equal to 1 by v minus 1 by u. Rearrange for 1 by v is equal to 1 by f plus 1 by u. Substitute the values. 1 by v is equal to 1 by 10 plus 1 by minus 25. So take the LCM and solve. We will get the answer as 3 by 50. So v is equal to 50 by 3 and 16.66 centimeter. Calculate the magnification, that is h dash by h is equal to v by u. So substitute and get the answer as minus 3.3 centimeter. The negative sign for h dash indicates that the image is inverted. So the next problem, a concave lens of focal length 15 cm forms an image 10 cm from the lens. How far is the object placed from the lens? Draw the ray diagram. Given f is equal to minus 15 cm, image distance is minus 10 cm. So write down the formula 1 by v minus 1 by u is equal to 1 by f. By substituting and rearranging, we will get 1 by u as minus 1 by 30 and u is equal to minus 30 centimeter. So we can see the diagram. Next problem. Find the focal length of the lens of power minus 2.0 diopter. What type of lens is this? Given p is equal to minus 2d, power of lens p is equal to 1 by f is equal to 1 by p. Substitute 1 by minus 2. The answer will be minus 0.5. If the focal length is negative, then that lens is concave lens or the diverging lens. Next problem. A doctor has prescribed a corrective lens of power plus 1.5 diopter. Find the focal length of the lens. Is the prescribed lens diverging or converging? So here what is given? The power of lens, that is 1.5 diopter. So in the problem the term is 1.5 d. D means diopter. It is the unit of the power. So the power is given as 1.5 diopter. Find the focal length of the lens. So f we have to find. Then we have to identify whether the lens is diverging or converging. If the lens is positive, then it is considered as a converging lens. If the focal length is negative, then it is considered as the diverging lens. So power of lens p is equal to 1 by f is equal to 1 by p. Substitute the value. Here 1.5 is there, that is decimal, so convert that to the whole number, then we can get 10 by 50. By simplifying, we will get 0.66. A convex lens has a positive focal length, therefore it is a convex lens or a converging lens. So what we have learned so far, from this, object distance are negative if on the same side as incident light. The image distances are positive for real image and negative for virtual images. Magnification is the image height divided by the object height, or we can consider image distance by object distance. The positive magnification means upright image, negative means inverted. The lens formula is 1 by v minus 1 by u is equal to 1 by f, where v is image distance, u is object distance, f is focal length. And f is positive for convex lens and f is negative for concave lens. Power of lens in diopters is the reciprocal of the focal length. Lens power indicates its ability to converge or diverge light. So here we completed the first chapter, that is light, reflection and refraction of grade 10. Thank you for watching and subscribe for more videos.